These are the solutions to the questions at the end of lesson 8.2. Now, number 1, we have this P is moving south at speed v. Now, we've got the sources of light. A is also moving down at speed v. B is moving northwards at speed v. And C is moving south at speed 2v. So all that matters is their relative velocities. The relative velocity of A to P is 0. B is v north minus v south is 2v. And C, 2v south minus v south is just v. So B is moving away the fastest. So it will have the lowest frequency. Then C, then A. So we have B is less than C, which is less than A, and that is option E. Number 2, lambda naught is 4.34 by 10 to the minus 7 meters. But their wavelength we're getting from the galaxy is 4.64 by 10 to the minus 7 meters. That means the difference is 0.3 by 10 to the minus 7 meters. So delta lambda over lambda naught is 0.3 over 4.34, because that's V over C. Leaving off the 10 to the minus 7s because they cancel out, we have 0.069. So that means V is 0.069 C, which is 0.069 times 3 by 10 to the 8, which is 2.07 by 10 to the 7 meters per second. The wavelength has shifted to be longer, so it is moving away. So that is D. Now, number 3, we have ideal polarizers. We always assume that polarizers are ideal. So that means when theta is 0, we get 100%. 4 is also E because, again, ideal polarizer. Theta is 90, and that gives 0%. Now, number 5, the change in wavelength over the stationary wavelength is 0.4%. So that means V over C is 0.4%. So that means V is 0.4% of 3 by 10 to the 8, which is 1.2 by 10 to the 6 meters per second. B, it is a greater wavelength, so it is receding. So that's what we call redshift, to a longer wavelength. Number 6, we have a red light. Now, if it's a red light, that means a stationary car would see it as red. So it means the wavelength to a stationary observer is 620 nanometers. But our very fast driver is seeing it as 540 nanometers. So that means the shift in wavelength would have had to be 80 nanometers. Now that over lambda naught is going to be 80 over 620, which is 0.129, and that would have to be V over C. So that means V would have to be 0.129 times C, which is 3.87 by 10 to the 7 meters per second, which is one fast car. Now, A. When we have Brewster's angle, we've got the light coming in, and this is Brewster's angle. Now the condition is, we'll call this the refracted angle, and we've got some reflection. And that reflected angle is going to be the same as Brewster's angle. and we've got a right angle there. So what we can say is the condition for Brewster's angle is that the refracted angle plus the reflected angle, which is in fact Brewster's angle, has to be 90 degrees. Now we know the refracted is 32, so that means Brewster's angle is 90 minus 32, which is 58 degrees. So then refractive index is tan 58, and that is 1.60. And number 8, we have the intensity is a half. So that means, so if that has gone down, then that means the electric field amplitude must have dropped by √2 because the intensity is proportional to electric field squared. So 5 over √2 gives us 3.54 volts per metre. And then 2, if we have E2 is E1 cos 45. So now, and that is just the cos rule for electric field. Remember, it becomes cos squared for intensity. So we have, 3.54 times cos 45, and that gives us 2.5 volts per metre.